This is Catherine Nightingale with Chattanooga State Community College, and this video is for Linear Algebra Section 6.3, Orthogonal Projections. In the last section, we talked about projecting a vector onto a line, and now in this new section, we're going to project a vector onto any subspace that has an orthogonal basis. So, now that we know how to project a vector onto a line, we can expand the idea to projecting a vector onto a subspace W in Rn. And we use the orthogonal decomposition theorem in order to find our orthogonal projection. And it's just an expansion of the formulas that we use to project a vector onto a line. The orthogonal decomposition theorem says that if we let W be a subspace of Rn, then each vector y in Rn can be written uniquely in the form y equals y hat plus z, where y hat is in W and z is in the set of vectors orthogonal to W. In fact, if u1 through up is any orthogonal basis of W, then we can find y hat just like we did for projecting a vector onto a line, where we do y dot u1 over u1 dot u1 times the vector u1. But now we have to add on y dot u2 over u2 dot u2 times the vector u2 all the way out to the subscript p. And z is still equal to y minus y hat. So here's our two formulas that you will need to write down and remember in order to do the homework for this section. And then just a notation thing, W with the perpendicular sign is the set of all vectors that are perpendicular to W. So that's what that notation means. Okay, the vector y hat is still called the orthogonal projection of y onto W, and it's often written as proj subscript W of y. So that's read as the orthogonal projection of y onto W. And when W is a one-dimensional subspace, the formula for y hat matches the formula that we gave in section 6.2 for projecting a vector onto a line. Here's a visual of the orthogonal projection. Think of a light shining down on the vector y, and then y hat ends up just being the shadow of y on your subspace. So you have the shadow of y is y hat, and it's actually in the subspace W, and then z is orthogonal to W, and what we do is we just break down y into y hat plus z. So there is your visual. There's y hat, the projection of y onto W. And now let's do a few practice problems using the orthogonal decomposition theorem. So practice problem 1, verify that u1, u2 is an orthogonal set, then find the orthogonal projection of y onto the subspace span of u1 and u2. Here's our given y, u1, and u2. And since u1 dot u2 equals 0, you can verify this. We conclude that u1, u2 is an orthogonal set. It's very easy to check when there's just two vectors because you just take their dot product and make sure it equals 0. So we've verified that u1, u2 is an orthogonal set. Now we want to find the orthogonal projection of y onto the span of u1, u2. Okay, I'm going to, for ease of notation, let W equal span of u1, u2. By the orthogonal decomposition theorem, the orthogonal projection of y onto W, or y hat, is going to be y dot u1 over u1 dot u1 times the vector u1 plus y dot u2 over u2 dot u2 times the vector u2. That's just straight from the theorem. So let's set it up. Here is our y dot u1 over u1 dot u1 times the vector u1. And now we add on y dot u2 over u2 dot u2 times the vector u2. And if we simplify that, we get 30 over 25 times the vector u1 plus negative 15 over 25 times the vector u2. And of course, always simplify your fractions when you're doing this. I left it in the form of what you would get if you just did the calculation of the line above. But when you go to add them up, you want to simplify. So we get 630. There's our y hat. So there's our orthogonal projection of y onto the span of u1, u2. So that's how we use the theorem to find y hat. Okay, here's another practice problem. Let W be the subspace spanned by u1, u2, and write y as the sum of a vector in W and a vector orthogonal to W. Now we have a different y, u1, and u2 than we did in the previous problem. So first thing we want to do is check that u1, u2 is an orthogonal set. Otherwise we can't use the theorem. So we just really quickly take the dot product. u1 dot u2 equals 0, and it's an orthogonal set. So now we can use the theorem. And remember, the theorem not only tells us how to find y hat, but it tells us how to find z. Z equals y minus y hat. And z is always orthogonal to the plane W, or subspace W. It doesn't have to be a plane. Alright, so now let's actually apply the theorem. Write y as the sum of a vector in W and a vector orthogonal to W. Okay, so here is what I just put up on the screen. Y hat equals y dot u1 over u1 dot u1 times the vector u1 plus y dot u2 over u2 dot u2 times the vector u2. That was written on the previous screen, and we've just applied it to the vectors we were given. So now let's calculate it. So we get 2 times the vector u1 plus 1/2 times the vector u2, and that equals 3/2, 7/2, 1. So there is our y hat. That is in W, and it's the orthogonal projection of y onto W. So that's actually sitting in the subspace W as the shadow underneath the vector y. Okay, now we want z, and z equals y minus y hat. So we have y is negative 143, y hat is 3/2, 7/2, 1. So that gives us negative 5/2, 1/2, and 2. So now we have y hat and we have z, and our goal is to write y as the sum of a vector in W and a vector orthogonal to W. So y equals y hat plus z. Y hat is in W, z is perpendicular to W, and so we've done exactly as the problem asks. You would actually write the vector y hat and the vector z that you found in the problem. Alright, one neat application of these projections is distance. So the closest point to vector y in the subspace W is the orthogonal projection y hat. And the distance from y to W is defined to be the distance between y and y hat. If y is in W, then y hat will equal y, and the distance will be 0. So that makes a lot of sense, because if y is actually in the subspace, then the distance between the vector and the subspace should be 0. So we're going to use this to find some distance. Here's our exercise. Find the closest point to vector y in the subspace W spanned by v1, v2, and v3. Then find the distance from y to W. So here's our vectors. Our vectors are actually sitting in R4 in this problem because they each have 4 entries. And what we want to do is note that all the possible dot products, v1.v2, v1.v3, and v2.v3 are 0, so we can use the orthogonal decomposition theorem. We can use the formula for finding y hat. Now, the reason I always check this is because the theorem only applies to an orthogonal basis. So we always want to just verify that the theorem applies. Okay. Now we want to find the closest point to vector y in the subspace W. So we're going to use the formula for y hat. It's y dot v1 over v1 dot v1 times vector v1 plus y dot v2 over v2 dot v2 times vector v2 plus y dot v3 over v3 dot v3 times vector v3. Okay, let's plug it all in. So we have 1/3 times vector v1 plus 14/3 times vector v2 minus 5/3 times vector v3. You should go through and verify this to make sure that these are the same dot products as what you get. And this equals 5236. So there's our y hat, and that is the closest point to vector y in the subspace W. And that will always be the case. Y hat will always be the closest point to y in W. Okay, now we want to find the distance from y to W. Okay, so we have y hat, we have y, and the distance was defined to be the distance between them. So distance from y to W is the length of y minus y hat, or distance between them. So we have y hat equals 5236, and the distance formula we talked about in section 6.1, it's equal to the square root of the first entries subtracted and then squared, second entries subtracted and squared, third entries subtract and square, and so on. So we have 3 minus 5 squared, 4 minus 2 squared, 5 minus 3 squared, and 6 minus 6 squared. If I simplify this, I get the square root of 12, or 2 square root of 3, or 3.4641. WebWork should accept any of these answers. Remember to do square root in WebWork, you do SQRT parentheses 12, or whatever number you have underneath your square root. That's it for section 6.3. You have orthogonal decomposition, projection onto a subspace, finding a vector orthogonal to a subspace, and finding distance.